Hey everyone, in this video I'll be going over the solutions to FRQ problem number 9. In this problem we're looking at a 0.2 kilogram mass that's sliding on a horizontal air track, so there's very little friction. In fact, the problem just says to assume that there is no friction between the block and the air track, and it's going to collide with a 1.3 kilogram mass over on the right that's attached to a spring. Once that collision happens, the two blocks will stick together and then they'll start oscillating back and forth on the spring. So when you see a problem like this, one thing you'll want to be able to do is to sort of separate it in your mind into two separate events. So in the first case, we have the collision itself, which we can analyze using ideas about momentum. And then after the collision happens, the two masses will start oscillating back and forth on the spring, and we can analyze that separately once we know how fast they're going after the collision. All right, so let's go ahead and start going through the solutions here. So part A asks us to calculate the linear momentum and the kinetic energy of the block before the collision. So that's just as it's pictured up above. So the first part is the linear momentum. You want to remember that momentum is defined as mass times velocity. So it'll be 0.2 kilograms times 3 meters per second. So that gives a magnitude of the momentum as 0.6 kilogram meters per second. Second question is to find the kinetic energy. Kinetic energy is calculated as 1/2 the mass times velocity squared. So that'll be 1/2 times 0.2 kilograms times 3.0 meters per second squared. That comes out to 0.9 joules. Quick side note, you don't need it for this problem, but one thing that may be useful to remember is this relationship between kinetic energy and momentum. We can also say kinetic energy is momentum squared divided by 2 times the mass. If you plug in P equals mv in this equation, you should see that it ends up giving you 1/2 mv squared. All right, so moving on to part B, we want to calculate the linear momentum and the kinetic energy once more, but this time we're looking at the values of those those quantities immediately after the collision. All right, so the first question is the linear momentum. Actually, don't overthink this. If you remember, the way we analyze collisions is using the fact that momentum is always conserved in a collision. So that means the momentum after the collision must be equal to the momentum before the collision. So that's just 0.6 kilogram meters per second, nothing to calculate there. However, for part 2, to get the kinetic energy, we do need to know how fast the two blocks will move immediately after the collision. So the velocity is going to change. All right, so we can say that the momentum after the collision, which is 0.6 kilogram meters per second, is equal to mass times velocity, but this time the mass that is moving is the combined mass of the two objects. So 0.2 plus 1.3 kilograms. And it's moving with some final velocity. So we take 0.6 kilogram meters per second, divide that by 1.5 kilograms, and we get a velocity of 0.4 meters per second. So we plug that into the formula for kinetic energy. We also have to remember to use the correct mass. We have a total of 1.5 kilograms of mass in motion, and they're moving at 0.4 meters per second. So we plug those in, we get a kinetic energy after the collision of only 0.12 joules. So we should expect the kinetic energy to be less than it was before the collision, because by definition, a collision in which two objects stick together is an inelastic collision, and in an inelastic collision, kinetic energy is always lost. All right, so part C asks us to find the amplitude of the harmonic motion. So once this collision happens, the two blocks will continue to the right, they'll slow down as the spring compresses, and then start accelerating back to the left, and then since there's no friction, they will just oscillate back and forth forever on this table, and we want to know the amplitude of that oscillation. In other words, let me put the new picture down here. So let's say the blocks right now are shown exactly at the equilibrium position, so the spring is not compressed, the blocks have just collided, and they're going to continue to the right and then go back to the left, and they'll end up oscillating back and forth symmetrically about this position. Okay, so we want to know the amplitude, which is defined as this distance here, and I'm going to call it x max. All right, so one thing we know about this kind of harmonic motion is if we think about this in terms of what's happening with the energy, energy is constantly alternating back and forth between two forms. Those forms are kinetic energy and elastic potential energy. So when the block is at this position, right in the middle, there is no elastic potential energy, so we can say UE equals 0, but the masses are going to have the maximum kinetic energy. When they reach the two edges, so maybe out here, the elastic potential energy in the spring is maximum because the spring is compressed as far as it gets. But the masses come momentarily to a stop, so the kinetic energy will be 0. So what we're going to do is compare the energies at these 2 points. We'll say the maximum kinetic energy must equal the maximum elastic potential energy. All right, so notice that we actually know the maximum kinetic energy because that's what we just calculated in part B. We calculated the kinetic energy immediately after the collision, so that means the spring is not compressed. So this value is 0.12 joules. So that means the maximum elastic potential energy must also be 0.12 joules. All right, so the only thing we need now is this formula for calculating the elastic potential energy, and that is 1/2 times the spring constant K times x squared. All right, so the maximum value happens when x is at its maximum value. So I can say 1/2 times K, which is 100, times x max squared is equal to 0.12 joules. If I solve this, I end up getting the maximum displacement of the spring, which is also going to be the amplitude of the oscillation, to be about 0.049 meters. 0.05 would be close enough if you put that as your answer. All right, so there's one final part. Part D asks you to calculate the period of the harmonic motion. In other words, how much time does it take this mass spring system to complete one oscillation? This is a problem where you really should just look up the formula. This is a plug and chug problem here. So you should have this on your official formula sheet. The period for a mass spring oscillation is given by the formula 2 pi times the square root of m divided by k. So all we have to do here is plug in the correct values. The mass is 1.5 kilograms. The spring constant is 100 newtons per meter. So if we work this out, we get a period of 0.77 seconds. All right, so that does it for this problem. This has some material that we haven't been seeing lately in FRQ questions, so hopefully this stuff is starting to come back and sound a little familiar. If you have any other questions, as always, please let me know. Thanks for watching.